In this video, we're going to look at the AND law for independent events. Let's start off by looking at what independent events are. Two events are said to be independent if the outcome of one doesn't affect the outcome of the other. Let's look at what that means. I've got a bag of shapes here. We can see there are 7 shapes in total. I've got 2 triangles, 3 squares and 2 circles. So if I chose a shape at random, we could say the probability of a triangle would be 2 out of 7. There are 2 triangles and 7 shapes. The probability of a square, well, we can see there are 3 squares out of a 7. And the probability of a circle, well, we have 2 circles out of 7 shapes. We saw in the last video that all of these probabilities will sum to give 1. If we wanted to look, for example, now at the probability of a triangle or a square, we would simply go ahead and add the probabilities. This just gives me now the probability of a triangle plus the probability of a square. These are mutually exclusive events. We can say that this is going to be 2 over 7 plus now the probability of square, which is 3 over 7, which gives us 5 over 7. So in this example, we've got or. So I'm choosing now a triangle or a square. What I'm going to do is look at choosing 2 shapes out, and we're going to look at what independent events would look like, and then we're going to look at something called conditional probability. In conditional probability, the outcome of one event will affect the outcome of the other. So I'm going to choose, and this is going to be my experiment, I'm going to choose 2 shapes. So 2 shapes are going to be picked at random from the bag. We're going to look at the first example, and this is with replacement. So we're going to write down replacement. Replacement and non-replacement is just one way of showing independent events and also the conditional probability. So I'm going to put now non-replacement. So if we replace them, let's put this in, if we replace them, the events will be independent. If we don't, we will have conditional probability. So let's set up a scenario. What I'm going to do is look at the probability of choosing a square and a triangle with my 2 picks. So if we look at the first event, the probability of a square. So the probability of a square, we know that there are 3 squares out of 7. So let's say I chose a shape at random, and let's say it was a square. I took it out, I looked at it, I noted what it was, and then I replaced it. The second event is going to be the probability of a triangle, and we can see now in the bag the probability of a triangle, there are going to be 2 triangles out of 7. So by replacing the first shape, I've now got independent events. The probability of the triangle has not changed as a result of the outcome of the first event. Let's now look at not replacing. So we've got the probability of a square and a triangle. On the first one, we can say now the probability of a square we know is going to be 3 sevens. So let's say I chose one now, and we picked one at random, and it was a square. So let's say we chose a square. At this stage, I'm not going to replace the square. We can see the outcome of this first event will affect the next event. So we can say at this stage, the probability of a triangle has changed. So the outcome of the first event, by not replacing it, will affect the outcome of the second. We can see now triangles, we've got 2, but we only have 6 shapes in the bag. We could of course write that as 1/3, but we can see that the triangle has gone from 2 sevenths to 2 over 6. If I chose another shape, for example, and I chose a circle, then this too will affect on the next pull that I do, or the next event. We can see there are 2 out of 5. So this is now an example of conditional probability, because we're not replacing, but if we keep putting them back in, the probabilities are not going to change based on what's happened in previous events. So that's the difference. What we're looking at in this video is replacement or independent events. Replacement and non-replacement is just one example of showing the difference between independent events and the conditional probability. So let's go to our cards, our dice and our coin. If I had a deck of cards, there are 52 cards in the deck. If I wanted now to pull the ace of hearts, the probability of the ace of hearts is going to be equal to 1. There's one ace of hearts out of 52 cards. So let's say I now drew one card at random, and it was, let's say, and I'll just do a quick drawing, let's say that I had the 3 of diamonds. If I put this card back, the probability of the ace of hearts on the next one would still be 1 out of 52. If I didn't put it back, the probability of the ace of hearts would become 1. There's still only one ace of hearts, but there are only 51 cards. If I took another card, let's say this time we had now the 4, let's say we've got the 4 of hearts. If I took this out, the probability now that the ace of hearts would come on the next one, there's still only one, but we're down to 50 cards. So by not putting these back, we have now conditional probability. They're no longer independent events. If we put it back, they would be independent. Let's say now with our fair 6-sided dice, I'm going to look at rolling the probability of a number 4 and a number 3 if I roll this twice. So if we think about this now, I'm going to roll it once. So let's just go ahead and roll this. So I'm going to roll it once. Then I note what I've got. If I roll it again, it doesn't matter what I did the last time. These are independent events. It's not as if I'm now scrubbing off the 4 or I'm scrubbing off the 1. These are independent events. So the probability of rolling a 4 followed by a 3, we call these independent. They do not affect each other. If we look at this one, if I said now the probability of a head and a head, we can see by flipping the coin, it's not going to change. So if we do that, let's just do that, and then we'll stop it. Each time we do this, it doesn't alter, nothing's changing. These would be independent events. So the probability of a head and a tail are independent. Okay, let's work through some examples and look at possible independent and non-independent or dependent events. So it says for each pair of events, A and B listed below, decide whether or not it's likely that the events are independent. So A and B, it rains today, it rains tomorrow. What we're looking at now is, does one of these events influence, or the outcome of one of these events influence the outcome of the next? If it's raining today, the probability of it raining tomorrow will generally increase. So we would say that these are not independent. So if we just put this here, so these are not. So we can see now if it rains for a whole week, the probability of it raining the next day will have increased. It rains on Monday this week, it rains on Monday next week. I would say that these are independent. All we're trading on is this day being the same. A week apart, the weather can be vastly different. I would say if it rains this or it's sunny this Saturday, the probability of it being sunny next Saturday wouldn't have increased or decreased as a result of it being sunny on Saturday. So I would say that these are independent. If we look at this one, a die is rolled twice. The first roll shows a 3, the second roll shows a 5. We've already looked at these. These are independent. What we get on the first doesn't influence what we get on the second. If we look at the next one, a baby is born, its left eye is blue is one event, its right eye is blue. So we've got two different events. If its right eye is blue, the probability that its left eye is going to be blue has now increased, and vice versa. So these now are going to be these are not independent. Some babies, of course, have different colour eyes, but with a baby being born with a left eye blue, it's now increasing the chances of the right eye being blue. And in the same way, if it's born with a right eye that's blue, it's increasing the chances now of the left eye being blue. So they are not independent. Joshua and James are brothers. A, Joshua catches measles. B, James catches measles. We assume that these two live together. If one catches it, it will increase the chances of the other catching it. So these are not independent. If you go to school and everyone's got a cold, the probability that you're going to get a cold will increase. So they are not independent events. If we look at the next one, Daniel cycles to school. Daniel's bicycle has a puncture. Daniel is late for school. If he has a puncture, it's likely to increase the chances that he's going to be late. So we would say that these would not be independent. So all we've done is considered, is Daniel's bicycle having a puncture going to affect him being late for school? There is a good argument to have if you switch these over. Daniel being late for school and Daniel's bike having a puncture. If he's late for school, does it increase his chances of having a puncture on his bicycle? We'll look at discussing that later on in another video, but hopefully it gives you some food for thought. So in this case, Daniel's bicycle having a puncture and him being late for school, these would not be independent. So let's look at how we work out the probability of two or more events happening. We saw with the oral, and let's just write this in, the probability for mutually exclusive events, the probability of A or B was equal to the probability of A plus the probability of B. And we just looked at adding them. And we've seen an example of that time and time again. For independent events, we say the probability of A and B is going to be equal to the probability of A multiplied by the probability of B. What I'm going to do is construct a scenario where we are given a choice to save our lives. What we're going to have is a fair coin, so a fair coin, and we're going to have a fair six-sided dice. So fair six-sided dice, so six-sided dice. We're given the opportunity to choose one of these to save our lives. What we're going to go for is the following. We're going to be asked if we want to take flipping, and I'll write this here, flip, and we will go for five, we'll say five heads in a row. So 5 heads in a row. And on this one, we will say rolling. So rolling now 2, and we'll say 2 number 3s in a row. So which would you take to save your life? You're given this opportunity and someone says, I'll let you out of here if you can get one of these right. So let's look at this one. The probability of flipping 5 heads in a row. The probability of flipping 1 head in a row, so the probability of a head is going to be 1/2. It's a fair coin. We've either got heads or tails. So what I'm going to write now is the probability of head. Then we're going to have and head. And this is writing it out long form. And we've got and another head, and another head. And just writing this out. And we can, of course, use different notation. The different notation comes in at a slightly higher level. So I'm just going to write it out like so. So how many more do we need? We need, I think we got enough. We got 1, 2, 3, 4, 5. Okay, so what we're going to do is look at flipping a head. If you flip a head once, you've got 1 in 2 chance. Doing it twice in a row increases the challenge. It's harder to do it. What we're going to actually look at now is the probability of all of this is going to be equal to the probability of a head multiplied by the probability of a head multiplied. As soon as we see the word and, we're going to multiply. If we see the word or, we're going to add. So what this is saying now is the following. Probability of a head, and we're multiplying. Now when we're multiplying fractions between 0 and 1, the number is going to get smaller. Therefore, the probability of it happening is going to be less. So what we've got is 1 over 2 times by 1 over 2. So 1 over 2 times by 1 over 2 is 1 over 4. Times it by 1 over 2 is 1 over 8. Times it by 1 over 2 is going to be now 1 over 16. Times by 1 over 2 is going to give us 1 over 32. What we could have said here, that this is going to be 1 over 2 to the power of 5. So the probability of me flipping a coin, a fair two-sided coin, 5 heads in a row is 1 out of 32. Let's look now at the probability of a number 3. The probability of a number 3 on a fair 6-sided dice is going to be 1 out of 6. So what we've got then is a probability of a 3 and now a 3. So if we look at this, this is saying that we're going to be multiplying. So this is a probability of a 3 multiplied by the probability of a 3. As soon as you see the word and, you're multiplying. So if we look at this, 1 out of 6 multiplied by 1 out of 6 That's going to give us 1 over 36. So we can see now 1 over 32, 1 over 36. We can see it's less likely, or the probability is lower of getting 2 3s in a row than it is to flip 5 heads in a row. This is higher, this is more likely. We can see the more of these we do, the harder it becomes. So if I said 6 of these in a row, it'd be 1 over 64. 7 is 1 over 128. So if you looked at now the probability, and I'm just going to use a different bit of notation here. The probability of let's go for a number 2 and a number 2 and a number 2 on a fair 6-sided dice. It'd be 1 over 6 multiplied by 1 over 6 multiplied by 1 over 6, which is going to be 1 over 216, or 1 over 6 to the power of 3. That's really, really tough to do it. So if you ever roll a fair 6-sided dice and you get 3 2s in a row, it's pretty hard. And as you see with the lottery, the first ball is 1 out of 49, 1 out of 48, 1 out of 47. As you're multiplying those fractions, the denominator is getting huge, and the likelihood of you getting more than 1 ball is massive, more than 2 balls is even less likely, and so on and so forth. So we can see now, if we want things to happen in a row and, it becomes less likely that it's going to happen. If we're adding them, it becomes more likely. So for example, if I said on this one, the probability of, let's go for the 6-sided fair dice, a 2 or a 5, well, that's just adding them. The probability of a 2 is 1 over 6. The probability of a 5 is 1 over 6, which is going to give us 2 over 6, or 1 over 3. If I said now the probability of a 2 and a 5, so in this case, we're doing 2 different events. So with this, we just got 1 event. That's easy. This is going to be 1 over 6 times by 1 over 6, which is going to be 1 over 36. So if I said you can now roll a 2 or a 5 with one go, nice and straightforward, 50-50 chance. If I said you can roll this twice, but you must get a 2 and you must get a 5, then it becomes 1 out of 36. So that's looking now at the difference between the two. So the or rule for mutually exclusive events, the and rule for independent events. So let's answer some questions. Let's go ahead and look at these. So it says, in a school, 20% of the children are colourblind and 10% are left-handed. If a child is selected at random, what are the probabilities that they are A, B and C? What I've got here are what we call tree diagrams. Often using tree diagrams can help us now with these and rules. So what I'm going to do is introduce the idea of a tree diagram, and we're going to have 2 different events. So what we're going to do is look at now the first event. The first event is now whether the child is colourblind or not. So what I'm going to have, event number 1, whether they're colourblind or not. Event 2 is going to be whatever hand they are. Are they left-handed or are they right-handed? So we might want to call this now vision, we might want to call this the hand. So what I'm going to is here have colourblind, and I'm going to put C just here. I'm going to use a bit of different notation, and on this one I'm going to put not colourblind, and we would say now that C not colourblind. So we know that 20% of the children are colourblind. 20% as a fraction is 20 over 100, or 1/5. So on this branch I'm going to put 1/5. All probabilities must sum to 1 if we're going to have colourblind or not colourblind. Therefore, the probability of not being colourblind must be 4/5. It's 1 minus this. So with a tree diagram, what we're going to have are these 2 branches always equaling 1. What I'm going to have here now is left-handed, and I could put left not, or I could put right-handed. It's entirely up to you. So if you wanted to put RH and LH, you could do. I would suggest any of these are perfectly fine. So on this one, we've got left-handed and we've got right-handed. So this is the second event. We can see that 10% are going to be left-handed, and that means that 90% are right-handed. So 1 out of 10 chance of being left-handed, and we can say 9 over 10 chance of being right-handed. These must equal 1. Left-handed, 1 out of 10, and then we've got right-handed, we've got now 9 out of 10. What we could have also done is a sample space. So we could have listed all of the possible outcomes. What I'm going to do is use the tree diagram to solve this problem. In part A, we need to find the probability that they're neither colourblind or left-handed. This is quite a tricky question for the first one. They're neither colourblind or left-handed. What we could do is work out some probabilities, or alternatively, we could use this to look at the one that satisfies this particular criteria. So what we could have had is colour-blinded and left-handed. We could have had colour-blind and right-handed, so let's put a right. We could have had not colour-blind and left-handed, and we could have had not colour-blind and right-handed. You can of course put L and not L just here. So they're neither colourblind or left-handed. So this one would be no good. So they're colourblind, and now these are left-handed. It only leaves us one possible scenario. So what we're going to do is go down this branch and then down this branch. So all I'm doing is saying now that this particular question is the probability that they're not colourblind and they're right-handed. And this is one particular approach that we could do. So all I do is follow the branches down, and this is going to be 4/5 multiplied by 9 over 10. We could simplify if we wanted to begin with, or we could just go straight ahead and cancel at the end. So 36 over 50, let's write this in. So 36 over 50, which would give me 18 over 25. That's a really tough question to start with. If we look at the next one, we want colourblind and left-handed. I think this would have been a nicer question to start with. So colourblind and left-handed, we can write here the probability of colourblind, and I'm going to use this notation again. We might have that. This is saying and, or if you like the intersection. Colourblind and left-handed, we simply follow the branches. As soon as the word and kicks in, we must use the multiplication. So let's go ahead and do that. So we're going to have now the probability of being colourblind. This is going to be 1/5, multiplied now by the left-handed, which is going to be 1/10. That's going to give me 1 in 50 chance. These are now, we're told, or we're not told that these are independent. They should be independent events. So colourblind and left-handed. Colourblind and left-handed, we followed this particular approach. Alternatively, you could have used these and just looked at the probability of each. Left-handed but not colourblind. So what we need to do is find that one. So if we think about it, left-handed and not colourblind, we're going to go down the not colourblind branch and the left-handed. So we can say now that this is going to be the probability of not colourblind and left-handed. So just jotting this down, and that's going to give us 4 over 5 multiplied by 1 over 10, which if we wanted to write it out would be 4 over 50, or we could simplify that to 2 over 25. So all we've done is looked at using the branches, and we've moved down them whichever route that we want. They're quite tough, tricky questions to begin with. Okay, let's look at another one. The spinner shown in the diagram has 8 sections of equal size. Each one is coloured white or black. The events B and W are B, the spinner lands on black, W, the spinner lands on white. In part A, we're asked to find the following probabilities. And in part B, it says if the spinner is spun twice, find the probabilities of the following outcomes. Okay, so what we're going to do is just go ahead and just look at these. So the first ones are very straightforward. So what we've got then are the following. We've got B, and we can see that these are the black ones. So 1, 2, 3, 4, 5. So we got 5 out of 8. So the probability of a black is 5 out of 8. Therefore, the probability of a white is 3 out of 8. And we can see that anyway. So let's now draw a tree diagram. You certainly don't have to, but you could do for these particular scenarios. So what we've got on the next one is the probability of a B and a B. So what I'm going to do here is the first thing, and I'm going to say this is going to be spin 1 and spin 2. So my first event now is spin 1. So let's put this here, spin 1, and this is spin 2. So we can see with spin 1, we get a black or a white. On spin 2, we get a black or a white. These are going to be independent as we're just starting over again. It's not as if we're taking one of the sections away. So we can see the probability of a black is 5/8. The probability of a white is 3/8. If you weren't shown the picture, you can tell it's 3/8 as these must be equal to 1. Okay, we put the same probability on here. We've got 5/8 and we got 3/8. If we look at this one, we've got 5/8 and we've got 3/8. If we wanted, we could do a sample space. So what we could have said, now looking at all of the possible outcomes of 2 spins, black and black, black and white, we could have said now white and black, and we could have said white and white. So those are all of the possible outcomes. So if you prefer, you can do a sample space. So let's have a look at this one right here. B and B. We simply follow up. We've got B and B. I see the word and, so we can say that that is going to be now the probability, and I'm just going to use the other notation. B and B is going to be 5/8 multiplied by 5/8, or if you like, 5/8 squared, which is going to give us 25/64. You could have simply taken now the sample space here. We know that the probability of black is going to be equal to 5/8. The probability of white is going to be equal to 3/8. So if we want black and black, we multiply these. Black and white, we multiply this one by this one. White and black, we multiply this one by this one, which is exactly the same as black and white. And then white and white, 3/8 times 3/8. So if we look at this one right here, white and white, we would go down here, white and white. So 3/8 times 3/8, which is going to give us 9/64. Black and white. So if we go black and white, we multiply these two. And then finally, white and black. We go this way and this way. So that's just asking us to find certain probabilities. In part B, it says, if the spunner is spun twice, find the probabilities of the following outcomes. So I like to look at this as a sample space. White is obtained both times. This is the only one now that satisfies this particular criteria. So what it's saying is the probability of white and white. As soon as I see this word and, I'm going to multiply. So this becomes 3/8 times 3/8, or 3/8 squared, which gives me 9/64. Remember, with your probabilities, they can either be fractions or decimals. A different colour is obtained on each spin. This is where we bring in the and rule and the or rule. So if we consider now, and all I'll do is look at the 2 possible scenarios. The 2 possible scenarios is a black followed by a white, or a white followed by a black. If you want to look at this on the tree diagram, a different colour is obtained. On the first one, we could have now our black and a white, or we could have our white and our black. So what we'd do is the following. We'd set this up, and in later videos we'll look at some tougher exam style questions. What we have here is the probability of black and white, or we have now the probability of white and black. So here I know that this is going to be the 5/8 times 3/8, 5/8 times by 3/8. This is exactly the same, it's just the other way around. 3/8 multiplied by 5/8. You could essentially say that it's 2 lots of each of these, or 2 lots of that particular fraction. So what we're going to have then, if I do these, I'm simply going to add them. So we're going to have 15/64. That now is the probability of a black and a white, plus now 15/64. If I add those together, I'm going to get 30/64. So 30 over 64, which we could simplify now. Dividing the numerator and the denominator by 2, that's going to be 15 over 32. So that's a probability now of getting different colours. We've used the AND rule because it's black and white or white and black. Okay, the same colour obtained on each spin. Well, if we look at that, that's fairly logical, and we can work two different ways with this. What we could do is work out black and black and add it to white and white, or what we could have said, well, that's the only scenario that we've got left, so let's put that, and it would be black and black, so let's see if we can go up there. Let's grab up a pen. Let's do that. It would be black and black, which comes up here, or we're going to have white and white. So if we look at this, and we'll look at it two different ways. There's a longer way to work it out, and if we do that, let's go ahead and do that. What this is saying now is the probability of black, and I'll go back to using and black, which is going to give us now 5 over 8 multiplied by 5 over 8. Then I've gone that route, or, so we can write or. So I'm going to add to that now the probability of white and white. So the probability of white and white, so white and white, and that's going to be 3 over 8, and then we're going to multiply that by 3 over 8. So that gives me now on here 25 over 64 plus 9 over 64, so let's write that on, which is going to give me 34 over 64. At this stage, I just want to stop things, because if we look across here, what we've got now is 30 over 64. We could have simply said it's 1 minus that probability, as these are the other two scenarios that might happen. We could have looked at other scenarios. Now, if we said on here, for example, the scenario where we didn't have white on both, we could work out white and subtract that away from 1, rather than doing black and black, black and white and black. So the probability that neither now were white, we would do white times by white and do 1 minus that. So the probability of not white and not white is 1 minus the probability of it being white and white. So as we can see, sometimes we're going to need to use both of the laws. Okay, let's just move on and look at where we were before. So what we've got, back to my bag, I'm now going to introduce a tree diagram. Let's do this, and we'll introduce a tree diagram, and this time we've got 3 branches. So we're going to do some picks, and these are going to be independent events. So what we're going to have is pick 1. So what we'll have, pick 1, so pick 1 and pick 2. We're going to choose 2 now of these shapes from the bag, and we're going to replace them. So if we look now, let's put on here, on the first pick, we've got a square, we've got a triangle, and we've got a circle. So square, triangle, circle. If I put it here, exactly the same, pick 2, square, triangle, circle. Square, triangle, circle. So all I'm doing is replicating this, and we can look at 2 different picks. So on the first one, we know from before that we have a total of 3 squares. So this would be the 3 out of 7. We've got 2 triangles, which is 2 over 7, and we've got 2 over 7 down here. Remember, all of these branches need to add up to 1. If I replace them, we're still on 3 over 7, we're still on 2 over 7, we're still on 2 over 7. If I look at this one, we're on 3 over 7, we're on now 2 over 7, and we're on 2 over 7, so 2 over 7. This one, 3 over 7, 2 over 7, and then we've got on here, we've got 2 over 7. You could argue now that it's easier to draw a sample space. So if we chose 2, what we could have is the following, and listing them out systematically: square, 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 then we'd have triangle, then we'd have square, circle. We would then go for, on the next one, we would do the triangle, and we would have square, we would have triangle and circle, and we would have, in fact, let's put this in order, let's make it look a little neater, we'll do triangle, triangle. So these are all of the possible outcomes of 2 spins. So we'd have triangle on the first one, triangle on the second one, triangle on the first one, then we'd have square, then we'd have triangle, then we'd have circle. If we did the circle, we'd have circle, 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 triangle, circle, square. So this is pick number 1 and this is pick number 2. So this is a sample space. That's a little slack with my writing out, but do make sure you've got them all. So if we said now on the first pick and then the second pick, we wanted now, let's write this down, probability of a square and a square. All we would do is follow this particular route. This would be 3 over 7 multiplied by 3 over 7. If we looked now at a square and a triangle, we'd follow this branch, square and triangle, and multiply those. We could look at all manner of different probabilities. We could look at the probability of not getting a circle and a circle by simply doing 1 minus getting a circle on the first and a circle on the second. So when we look at the exam questions, we'll spend a little more time. If we think about this now, what I'm going to do just to end the video before we go into the next one is look at if this was non-replacement, if I took them out. And what we'll do, we'll build up the tree diagram and look at conditional probability. So we've been looking at independent events, but what I'm going to do now is not replace them. So if on the first pick I chose a square, we would only have 2 squares left out of 6 shapes in here. We would still have 2 triangles, but we'd only have 6, and we'd still now have the 2 circles out of 6. If I chose a triangle on the first one, the squares, well, there are still 3 squares in there, and that would be 3 out of 6. If I chose a triangle on the first one, we're down by 1 triangle, so we'd have 1 over 6. There is still 2 out of 6 circles. So this now is non-replacement. We can see that all of these equal 1, 2 6s, 2 6s and 2 6s, 3 6, 1 6 and 2 6 give us 1. So if I took now a circle on the first one, there are still 3 squares out of 6. There are still 2 triangles out of 6, but there's only 1 circle. So we can see by not replacing them, it becomes conditional probability. Then on the next pick, if we didn't replace them, the denominator of this fraction would become 5. So this would become 1 out of 5, 2 out of 5, and 2 out of 5. So hopefully that gives you some scenario if we chose a square on that one. So that gives you a quick intro to the difference between independent events and conditional probability. In later videos we will look more conditional probability and then start to answer some exam style questions.